Thank you very much. Actually, let me maybe start by thanking Boban and Matteo and the organizers for putting this meeting together. At least for me, but I think for many of us, it's the first in-person meeting for a long time. So that's very nice to have it to meet again in person. I'll talk about perfect matchings in hyperfinite graphings, and I'll be writing the talk on the blackboard. If anyone thinks it's too small, please let me know, because I know the camera does not catch everything. So let me just say what a graphing is. So by a graphing, we mean a Borel graph on a standard Borel space, which is probability measure preserving. There's a probability measure preserving graph, Borel graph. On X nu, where X is a standard Borel space and nu is a probability measure. Yes, it means that whenever you have a Borel bijection whose graph is contained in the graph, then it preserves the measure. Examples, I will actually focus on examples which are generated by group action. So you can think about a finitely generated group and choose a set of generators, and then look at the Schreier graph. So join 2 points with an edge if there's one of the generators that maps one point to the other. And this is a graphing. And such a graphing is probability measure preserving if the action preserves measure, if all of the group elements preserve the measure. So
you mean move all the points, so you select the move edge?
Yes. Mm-hmm. So we're going today. I'm going to only talk about. Okay. Actually, you know what? Let me write what. Let me write what I just said. So examples. Include Schreier graph. Of group actions which are measure preserving. And in this case, it means that every group element preserves a measure as an automorph. In this slightly more general setting, we are going to assume that I'm going to be mostly concerned with graphs which are locally finite. So today, are locally finite, and even so the degree of every vertex is finite. And I'm just going to, I will be adding this almost everywhere because today during this talk I'm going to talk about measurable. I'm going to stick to the measurable context. So everything will be taken up to measure 0, and this almost everywhere just will appear to signalize that we are not really concerned with the sets defined everywhere, but up to measure 0. And also, let me say that the graphing is regular. Maybe n regular. If every vertex has degree exactly n. Is equal to n. So again, these examples of Schreier graphs, they are regular. N is twice the number of the generators. I will recall this connection with Borel decompositions and circle squaring. So just let me first recall what it means that two sets are equidecomposable. So given an action, gamma on a probability space, we say that two sets are gamma equidecomposable if we can partition one of them. Can be written as a finite union of subsets, and there are some group elements gamma I such that when we move these pieces by the appropriate elements, we get a partition of the seconds. And in such cases, we often obtain when we look at the Schreier graphing of gamma with respect to these elements gamma 1 to gamma n, then the question of the existence of equidecomposition is equivalent to the existence of a perfect matching in this Schreier graph restricted to the union of the two sets A and B. In the perfect matchings as objects, they are somehow well understood in finite combinatorics, and in the finite setting, especially in the bipartite setting, this is equivalent to many conditions, such as the Hall condition. But in the setting where we want obtain measurable decompositions, these finite combinatorial statements fail. So let me just say that in the finite context, finite bipartite graphs admit perfect matching. So I'm just going to write PM for perfect matching, if and only if they satisfy the Hall condition. For a subset of one of the sets of vertices bipartition. And in the measurable context, this fails. This can be used, for instance, in the composition context from the Banach-Tarski paradox, saying that there is a free action, PMP action. Of the free group with two generators on a probability space. And two sets which are equidecomposable but not equidecomposable with measurable pieces. Yes? Uh-huh. How about now? Okay. With measurable pieces. But also there is a well-known construction of Lackovich of even simpler graph. Let me recall that it's a very, in fact, very easy graph. There exists a two regular graphing. In the two regular case, any regular graph has a perfect matching. So I'll just say that without a measurable perfect matching. And the graph is defined on the set of edges, which is a disjoint union of two intervals. We choose a alpha, which is irrational, and we consider the graph, which as a subset of the product space is just this rectangle in the middle. That's a graph whose, so by this I mean that for every x here, these 2 points are its neighbors in the graphing. And it's a regular graph almost everywhere, but it doesn't admit a measurable perfect match. So in the case of measurable equidecompositions and measurable perfect matchings is a bit more complicated, but yet there are results to be proved, and I think that the proper context for this is that of at least for the example of Lackowicz's example, is that of hyperfinite graphing. So let me recall. I know what a hyperfinite graph is. We can define it just using the notion that we know of hyperfinite equivalence relation. So a graphing is hyperfinite if the induced equivalence relation of components is hyperfinite almost everywhere. These hyperfinite graphings, they were actually studied independently of hyperfinite equivalence relations, and they this was defined by Elek. And Schramm. And it has somehow surprising connections to computer science and something which is called testable properties. So this example of Lackowicz's is a hyperfinite graphing, obviously, because it's just well, maybe not obviously, but it's it looks like a Z on orbits, and it can be shown to be hyperfinite. Let me say that all amenable group actions induce hyperfinite graphings, and this is in the almost everywhere context. And then these hyperfinite graphings and perfect matchings come handy when we want to talk about measurable decompositions on the plane where the group of isometries is an amenable group. So there's a series of results on equidecompositions, measurable decompositions, and Borel equidecompositions in the plane, or even more general in the space, in the Euclidean spaces, which are all around the circle squaring. So this is the Lackovich circle squaring theorem, which says that the unit disk and the unit square are equidecomposable using translations. On the plane, and even more generally, two Borel sets which have the same positive measure, and there is some condition on the boundary. The topological boundary should not be too big, are equidecomposable in the Euclidean space using the translations only. And this was done a long time ago in the 90s, and more recently there is a series of results on measurable versions of this, which actually come somehow as results about measurable perfect matchings. So there's this result by Grabowski, Mate, and Pichurko, which is the measurable circle squaring. That says that these sets in the equidecomposition can be chosen to be measurable. Then there is the Borel circle squaring by Marx and Unger. And let me also mention the recent result by Mate, Noel, and Pichurko, which says that, which I think probably should be called Jordan circle squaring. It says that circle squaring is possible with sets which are Jordan measurable, and that means that the topological boundaries of these sets are measure zero. So these are somewhat very regular sets, Jordan. The bound on topological complexity is already here. It's, I think, these two. I don't think this is the same partition. I mean, honestly, this paper has been announced, but I haven't seen the proof yet. I'm not sure exactly what is the partition, but I think not necessarily.
I see. So you want the boundary.
Yes, could be some fractal set of measure zero. So I'm not sure if they use axiom of choice or not. Well, I think they are all quite large. Something like this already in the Lackovich construction is rather large. I'm not sure exactly, but 10 to the 100 sounds like an estimate. So this will be. More? Yes? No properties at all. They are non-measurable sets. They are, in a way, they are similar in this as in the Banach-Tarski paradox. So what Lackiewicz does is he works orbit by orbit. He constructs this action of z to some high power, such as the action of the F2 in the Banach-Tarski paradox, such that the sets that he starts with look somewhat nicely on each of the orbits, and then on each of the orbits, he just moves them around by finite distance and then gets the equidecomposition. All right. So, of course, thanks. So now, let me just say that the action or the group in the circle squaring is z to the power d for some large d. It's an amenable group, so these graphings are going to be hyperfinite. But as we saw in Lackiewicz's example, hyperfinite graphings do not necessarily admit perfect matchings. So there is one more thing that we should be assuming, and that is the number of ends. So a graph, or maybe let me say a graph is one-ended if after removal of any finite, well, I'm going to maybe talk about regular graphs. Is one-ended if after removal, if it remains connected after removal of any finite set. So z to the power z squared is one-ended. When you remove any finite set, then what you're left with is still connected. But z, or the bi-infinite line, is not one-ended. When you remove a vertex, then you're left with a disconnected set. So this is what seems to be the proper generality for a theorem. That says that any hyperfinite one-ended regular graphing admits a measurable perfect matching. If it remains connected, excuse me, it has only one infinite component. If it has only one infinite component, that's a good point. Mm-hmm. I'm not going to talk about too much about the proof of this, but I want to show you three types of applications of this to something which is once to the measurable circle squaring, then to some questions of Lyons and Nazarov, and then to some other questions in something which is called balance orientations, and I will try to define these now. It means that every vertex has the same degree. So one of the applications comes with something that might seems like a fancy notion, namely factor. Maybe before I speak about these applications, I wanted to make one comment that. So actually, we proved something slightly stronger that applies not only to regular graphings, but I will not. But I will not state it. Instead, I will try to convince you that some assumption is necessary, because one could suspect that simply any one-ended hyperfinite graphing has measurable perfect matching, and this is not true. So let me just give you this example. One-ended hyperfinite graphing without any measurable and the Lackovich example was two-ended, and that's how it should be called. But one can modify his example to get something which looks more or less like this. So this is what the connected components look like. These lines have the same property as the lines that appear in Lackovich graph. So these are two regular, these are lines, so the two regular graphs, they do not admit a measurable perfect matching. And then there are somehow other perpendicular lines with these gadgets inside, and this is a hyperfinite one-ended, because it's basically z-squared one-ended graphing that does not admit a measurable perfect matching. I will just say that lines as in Lackovich. And this is this does not it's a bipartite graph in the sense that it doesn't have odd cycles. One can modify this slightly to get a measurably bipartite graph when the pieces of the bipartition are measurable, but this does not admit measurable perfect matching. Because any perfect matching would have to actually choose two edges from each of these squares, and then remain a perfect matching on each of these vertical lines, which is impossible from Lackovich. Yes. Well, this is obtained from so Lackovich graph is actually obtained by looking at irrational rotation on the. It can be obtained by looking at the irrational rotation on the circle, and in that case, the fact that it does not admit a perfect matching follows from the fact that it acts ergodically on the edges of this irrational rotation. So a perfect matching would have to be invariant would be a set of edges that is invariant under this action, and then by ergodicity we'll have to have measure 0 or 1. And this is giving you a z action which does not have a perfect matching. To obtain this, you take two independent irrational rotations on the circle by two independent rational numbers, which gives you an action of z squared. And one of the pieces of this action, so this is where you don't have the gadgets. This would be simply z squared. And if you restrict it to the first rotation, then you get exactly the graphing from Lackovich. And then what you get is just you add these to the graph artificially. You replace every edge from the second generator by a finite set by such a gadget, and that's the construct. All right. Mm-hmm. Yes. It is. You can think about the Bernoulli shift. If your graph is a Cayley graph of a group, then you can think about the Bernoulli shift, and this is what people usually think about of spreading the graph.
So you are talking graph, but
this is actually simpler than the spreading. It's what I said to Philip. It comes from an action of z squared but not the shift, but actually an action on the circle. But the spreading, the typical spreading that people think of is the Bernoulli shift, and actually this. Okay, let me just figure out how to move this. Sorry. The perfect matchings in abstract graphs, as especially Cayley graphs, which are somehow spread out, they are called factors of IID perfect matchings. And this is a terminology which might sound a bit technical, but let me just say that the factor of Cayley graph is a probability measure on the set of all perfect matchings on the graph which is a factor in the sense it's a probability measure on the set on which we have an action of the group. So it's a space where it's a gamma. If the group is gamma, it's a gamma space, which is a factor of the Bernoulli shift. A natural measure on the Bernoulli shift. Now this sounds maybe slightly technical, but actually it's the same as simply the gamma this is the Bernoulli shift. Gamma is the group. But maybe in a slightly less, more familiar language, this is the same as a perfect, measurable perfect matching. In the Schreier graph of the Bernoulli shift, when we take the generators from the Cayley graph. With respect to so there was a theorem proved by Lyons and Nazarov who showed that for non-amenable groups then Cayley graphs, bipartite Cayley graphs, admit factors of IID perfect matching. Perfect matching. And there was a question. Oh, I'm sorry, I should be using this. And there was a question that was, I think, originally asked by Lyons and Nazarov, but it appeared in the form of this definition in a survey by Kekris and Marx. How about now? Which Cayley graphs admit a factor of IID perfect matchings? And for this question, in the one-ended, in the non-amenable case, this is what Lyons and Nazarov did. In the amenable case, there's a theorem that says that an amenable group can have only one or two ends. In the one end, this follows from that theorem that I mentioned. In the two ends, it turns out that it's not always the true, but this is what we can get. That if gamma is not isomorphic to the semi-direct product of Z acting on a finite group with odd size, then in that case, which also covers all the one-ended case, then any Cayley graph has a factor of IID perfect matchings. And in this case, where it is actually isomorphic to such a group, then actually no Cayley graph, bipartite. No bipartite Cayley graph admits a factor of IID perfect matchings. Okay, and maybe let me also, so this is one of the applications, but I started talking about measurable perfect matchings and circle squaring. So let me, fantastic, thanks. Let me tell you very quickly how the measurable circle squaring follows from this theorem. We actually have a couple of proofs. I will show you one way it follows from this regular case of the perfect match. So the graph that is behind the Lackovich construction is an action of z, let's say z squared. It's some z to the power d, and he constructs this action in such a way that the sets look very nicely on each orbit. This is more precisely if, let's say, A, B, let's say our subset of XX is a torus, for instance, and let's say that they have positive measure. Let's say it's 1/4 for simplicity. Then Lackovich, and under these are the circle and the disk and the square. Then Lackovich constructs an action which makes the sets so-called uniformly spread. And I will just make a picture because this is easy to draw. Uniformly spread sets in Z squared are of very very nice form. Namely, they on each orbit they look extremely regularly. Namely, in this case, they look like 2z on each 2z squared on each orbit. So and when I say they look like, I mean that Lackovich makes them equidecomposable with these two sets. One of them is this, and the other one is the red set. So this means that there is a bijection on each orbit. A on each orbit separately, A is equidecomposable with the blue set, and B is equidecomposable with the red set. But then the graph of distance, let's say 2 in the Cayley graph between the blue set and the red set is 4 regular, right? We have we have a 4 regular graph. So A and B. Well, I'm not showing the full proof. There are some subtleties here, but this is how it basically works. And then the graph is for regular and is one-ended and hyperfinite, because it's basically the action of z squared here. It's one-ended because z squared is one-ended, and this uniform spreadness makes it for regular, and then we can apply the slightly stronger version of the perfect matching theorem. So I think there's one more application to balanced orientations, but maybe I'll leave it out, and I think I'll stop here.